Hi, so I just wanted to do a quick video on what I've got running here. So this is a LED arrangement that is flashing. Currently it's configured to be flashing a SOS message in Morse code, so it just cycles that around and around indefinitely. But the neat thing about this circuit is that it's running without any programming whatsoever, short of one part that is technically programmable. So that's to say there's no microcontrollers. It's almost entirely discretely done, and I'm sure, given the part shortages that I'm guessing everyone is experiencing, just like I am at the moment, you probably appreciate why the significance of being able to do something like this. Now, this doesn't work for everything, of course. It's a technique that you'd be able to employ for pretty much any situation where you've got a repeating pattern that you need to generate. So this might be good, for instance, for a power up, a system power up sequencer, if you don't want to necessarily do that with a microcontroller. Or if you've got a repeated LED flashing pattern like I've got here, or potentially even playing back tones on a little piezo buzzer. This is applicable for all those scenarios, and the beauty about this is, because it's using generic jelly bean parts, as soon as something goes out of stock, you can very easily substitute an alternate with minimal to no redesign at all. And the additional part of this that's beautiful is that the part that does need to be programmed, because it's so generic, or because it's so ubiquitous, there are services from almost all suppliers that will actually ship these parts to you pre-programmed on the reel. So let's have a look at how this is actually done. Okay, so we're back over on the screen now, and just having a look at the schematic. Now this looks a little bit convoluted to start with, I would imagine, but let's just go through what's actually happening on this design one by one. So parts-wise, we've got basically a handful of Schmidt triggering inverters. We've got a 74 series 164 shift register. This is a serial in, parallel out shift register. And we've also got some SPI flash. Now, some of you might have already worked out what we're doing here, but before we get into that, just one thing to note, despite it looking quite convoluted, this solution all up is actually remarkably cheap for what you're actually able to do with it. So, typically the SPI flash at volume quantities, they can be had for 30 to 50 cents a piece, possibly even and that's dependent on size as well. If you can get much smaller parts as well, if your application allows it, it's going to be cheaper than that as well. This won't work with EEPROM, unfortunately. It does have to be SPI flash. Although this has quite honestly taken some inspiration from the old school technique of using address decoding to output, essentially using an EEPROM as a asynchronous state machine to set up to 8 outputs using a handful of address input. So this takes some inspiration from there, same sort of idea, but using it in a sequential manner instead. So you're looking at less than $1, absolute worst case for the SPI flash. The 74 series logic at volume, again, it can be had for less than 10 cents a pop. You'll probably do either a hex inverter pack or 2 dual inverting Schmidt trigger packs, and the shift register is going to be a similar amount as well. And then that's your overall solution. There might be an ancillary drive circuitry for whatever else you need to do. In this case, I'm just driving this LED directly out of the serial output of the flash device. But there's obviously an option here that you can isolate it with a MOSFET and get a little bit better drive strength out of it. So the basic premise of what we're abusing here is actually the fact that the read function on the in the JetX specification, governed by the JetX specification, and the read commands for SPI flash is hex 3, which amounts to effectively a pulse, a single pulse that gets that occupies the lowest 2 bits in the 8-bit command word. And this circuit, if you ignore the flash part, these 4 components here, or these four ICs here, are really what's managing all of that. So breaking this down, all we've got is basically a clock source, and we generate a frequency that is that corresponds to how quickly we want to step through the flash array, each bit within the memory bank, and we then invert that signal for utilitarian purposes, which will make sense in a second. And essentially, what we're doing is we're just generating a read pulse at the start of when we apply power to this thing. That is. It's not coupled, so this does need to be tuned to some extent, but it is effectively it's tuned to occupy the same pulse width as 2 bits. And then the reason why we invert the clock is because we want to make sure that when we're delaying this pulse, so that's maybe I'll explain it this way instead. This pulse, because it's going to on its own occupy 2 bits at the start of power being applied. We need to delay that by, in this case, 6 bits, so that we can occupy the last 2. And that's where this shift register comes in. So that's what's you basically tap off how much of a delay you want. So this is a pipe delay, or a different configuration of a ripple counter, effectively. And the reason why we invert the clock is because we want to make sure that this shift register is effectively preparing this read pulse on a different edge to where the SPI flash is expecting to pick it up. So what this basically manifests as then is we have something that looks like this. So this is just an LT spice. Now the values inside this schematic they don't match what's on the Altium view here, simply because in practicality these components are a little bit they behave differently to what the Spice World models them as. So there is a little bit of tuning that needs to take place here, and I'll discuss how possible ways to actually get around that in a second. However, the gist of it is this, basically. So you can see, matching the read pulse here, read instruction of 3, we have a delayed pulse, and that corresponds to bit 6 and bit 7 on the rising edge. So that's the basic premise. This pulse width doesn't need to be terribly accurate, so there's no reason why you can't extend this out a little bit further. What that will simply do is it will occupy this address space. The only thing that you need to be careful of, however, is that because the most significant bits are going to be set, you need to make sure that if you do extend that pulse width further out, that is valid memory, a valid address for your particular flash part. So say if you're using a 1 megabit flash ROM that has a 3-byte addressing system, but it doesn't have a valid address beyond the 17th and 18th bits or something. I don't know if those numbers work out, but just in my head, just off the top of my head, I'm speaking. You then potentially run into an issue where you're trying to address invalid memory, and the SPI flash won't work, or it won't respond by clocking out data. So that's the only thing to be careful of, which is why you might want some tight tolerancing on this pulse width reasonably. But if you don't care about that, or you select your EEPROM, your flash part carefully, then you can be a lot sloppier with that pulse width, and it's a lot more impervious to component tolerances. So that little tidbit. But if you do need to manage this quite repeatably, another way to do that, just because I'm trying to reduce part variance here, keep it as simple as possible from the BOM perspective, I'm just using another cell of the inverter basically to generate that one shot, that monostable. But there's absolutely no reason why you couldn't substitute this for a 555 timer, and that will allow you much tighter control over how wide that window is, and consequently, if you change from one inverter from one manufacturer to another, you potentially won't have to play around as much with these with the passive, the tuning of the oscillators and the rise times and whatnot. So yeah, there's ways around that, but I think for my applications, at least in this particular case, this works perfectly fine. The other nice thing about this is because it's a flash array, effectively, you're able to put arbitrary data in this, right? So you can very, very finely adjust how quickly the data is clocked out of the and hence its playback rate out of the output pin, simply by changing the clock speed on this input. So if you need particularly low frequency output, but you have a long record to play, you can potentially, some of these parts you can actually clock down to DC. Not the one that I'm using in particular here. On it doesn't match the part number here, but the one that I've got in my on the physical breadboard at the moment is a Macronix 25 MX25 series part. So that one only clocks down to 10 kilohertz. But there are SPI flash parts that will be happy to take down to DC at their clock rate. So if you have potentially days of data to play back, you could, there's nothing stopping you from reducing the clock speed and effectively going down to a resolution of 1 bit per bit, essentially, on the output. So in my case, because I've got that minimum clock rate, I've got each physical bit in each behavioral bit that I've got coming out of this this flash part corresponds to, I think at the moment it's configured to 4 bytes in the EEPROM, in the flash. But you've got total flexibility of how you want to do it. You can pad the data out, and the other beauty of this is, and this is something that you need to be careful of when you spec these the SPI ROMs. You need to make sure you pick one that actually has address rollover support. So that is when you're indefinitely supplying a clock to it, the flash part will essentially roll back over to address 0 once it gets to the end of its read. So this part does do that, and you effectively then have something that will loop indefinitely as long as you're supplying it with a clock. So some really, really neat things that you can that are leverageable from an architecture like this. Like I said, if any of these parts become obsolete, or out of stock, long lead time, they're very, very easy to substitute. The flash parts you can get pre-programmed from DigiKey, Mouser, etc., or the manufacturer directly. So there's no problems there. You don't even have to program this board yourself during production. And all in all, yeah, just I think it's a neat way of doing it. There's other potentials for expansion here as well. Like we're just doing a basic read operation on this. So, but there are quad SPI output versions of these. There are flash chips that support up to dual or quad data output. So if you want to get a little bit more sophisticated, you could actually do something like high-zetting the output of the shift register. Once it's clocked in that read pulse, you can gate that signal, and once you actually start clocking the data, you high-Z that, and then your input becomes an output then. And if you structure the data that's stored within the flash device correctly or appropriately, you can have up to 4 independent channels of control out of this. So there's nothing stopping you from potentially using this as a H-bridge gate driver as well, for instance. Obviously there's better parts to be able to do that, but depending on your application, similar cases where you need to have 4 independent channels of control in a synchronous manner. That could be one way to do it. Obviously, you know, the addressing is a little bit more complex at that point, so you'll probably need to do things like pulse width masking. So you know, you generate multiple pulse widths and then and or them together to generate the pulse that you want. But you know, depending on how risk averse you are, that might actually make sense. But you know, there's just a few ideas there. So yeah, hopefully that's helpful to someone out there. Catch you guys next time.